And let's go right to a chemistry review. Okay, so the first thing we're going to talk about here in our review is matter. So we said matter is anything that has mass or volume. Now, really more, we were interested in a couple of different things. So with respect to matter, let's talk about the very last thing we actually did in the chemistry unit, which makes more sense to start with now. It's classifying matter. Okay, so the very last thing we did was we classified matter into 3 categories. The first one would have been elements. And this was one type of atom. So already having done the periodic table, we should be a little familiar with this already. So something like we had calcium, we'd say that was an atom. Or, I don't know, iron was an atom. We could also have some of those diatomic gases. So if it was F2, I know we have 2 atoms there, but still is only one type of atom. So that would be our elements. The next type we classified as was compounds. Come on. So compounds was the next one, and that's where we put these together. So we have 2 or more types of atoms. Some examples might be that one, NaCl, or water, or, I don't know, iron 2 chloride sulfide. Anyway, so those are more than one type of atom. The last thing we classified as was a mixture, and this is more than one type of compound. So if you had something like salt water, you would know that it's made of salt and water. So clearly it has more than one type of matter. Maybe something like a pizza or garbage. Again, you look at that type of matter and you see a whole bunch of different stuff. So classifying matter, that was pretty much like, I know it was the last thing we did. The only reason I did it last was so that we'd already be familiar with these names and formulas a little bit. And I don't know, hopefully that made it a little easier on you. But now that we're familiar with it, it's probably the best place to start off. So anyway, that was the first thing we did with classifying matter. The next thing we did, or even the kind of the first thing we did, was keep this as a matter topic here, or heading. The next thing we did was we looked at physical and chemical properties. Now remember that when we were doing this stuff, we did physical and chemical properties, and then we also then looked at physical and chemical changes. So there was kind of like 2 different things on the go here. So if we're talking about physical properties, again, feel free to shorthand anything you want. We were talking about characteristics or qualities you can sense with your, or describe is a better word. You can describe with your 5 senses. What we were after is kind of like, you know, the state of something. That's, you would see it, right? Solid, liquid, or gas. The color, and that would be something you could see. If there was an odor, maybe it smelled funny. I don't know. It was hard. That would be you touching it. Or it was brittle. Or it breaks in part. Anyway, those are all things that you can figure out using your senses. Physical properties. And we also had chemical properties. And these are things that you can only observe doing an experiment. Found during experimentation. So, you know, you got an unknown substance in your hand. and you're trying to find out different things about it, like does it react with water? How does it react with water? Does it react with air? How does it react with air? Does it explode? Is it flammable? Is it combustible? Those are all things, properties you find out when you actually start to do an experiment. So just to put a couple in, combustible, or let's just put, does it light on fire? Question. The board became small on my screen. The board did? I don't know what to do there for you. Did you click any buttons? Maybe you can zoom in. Control plus will help you zoom in on that. Does it light on fire? Does it explode? Like, I don't know. I'm not sure exactly what. But again, it's like you got to go through some kind of test there to figure out, if it does anything. Maybe it does nothing. That's a reaction too, I suppose. So those are all physical and chemical properties. Easy ones. And of course, we're going to apply this here in a second. Things you describe using your senses. And then the other one is found during experimentation. Sorry, one sec here. Oh, nice. You're welcome. Okay, kind of wrapping up matter, if you will, sort of a category, again, onto its own. We looked at chemical and physical properties. Changes. Not properties, we just did that. So let's talk about changes here. This would be number 3. Oh, man. Physical and chemical changes. So this is getting more into reaction and things like that. Maybe a little more exciting, if you will. A physical change. This was kind of a boring one, if you will. It's like you do something, but you still have the same substance. So let's put the same substance remains after, I hate to call it an experiment, but we'll call it that. For instance, you take a piece of paper, you rip it in half. That's your experiment. You still got paper, but now you just got 2 pieces of paper. So that would be a physical change. You start with paper, you end it with paper. Or a carrot. You snap it in half, you got 2 carrots. Or you take sugar and you put it into water. Okay, yeah, now sure, the sugar is dissolved, but you still have sugar afterwards. So the same substance remains after experimentation. So let's put a change of state or dissolving. So those are the most exciting ones. Chemical changes are a little more exciting. Chemical changes, a new substance is formed. I think I might leak onto the next slide here because there were sort of 4 clues. 4 clues that this had happened, or has happened, whatever. So your chemical change clues. A change in color. Together, suddenly you got a different colored liquid. So a change in color. A solid forms. That was something if we were in the class, we'd do a little more with. Gas or bubbles form. So you put baking soda and vinegar together, and you can see that thing bubbling. That's a chemical change. And the last one is heat or light is given off. So you light a match, it burns. There it is. Now there's a rule of thumb to help you guys, because I think on the exam there's just like a a bunch of these, if you will. You just got to classify them. So chemical changes are hard to reverse. So that's what we kind of decide. So if I said baking, you got some toast. Is toasting bread a chemical or physical change? You're probably thinking, okay, well, you start with bread, you end with bread. It's probably just physical change. Well, ask yourselves, can you take toasted bread? Can you take toast and turn it back into bread easily? Yeah, no, you can't. So that means it would actually be a chemical change, hard to reverse. You know, if you baked a cake, could you take the cake and turn it back into those ingredients? Probably not very easily. So that would also be a chemical change. All right. Okay, so that sort of wraps up the first part here, which is all about matter. Now, the second part we'll transition to, we'll call the periodic table, because we spent basically the rest of this unit looking at the periodic table. Periodic table. Okay, so maybe it wouldn't be the worst thing in the world here for me to actually open up the periodic table. Again, here I linked one for you guys. This one's not into color, and coloring was one of our important things that we should be doing. So maybe this periodic table, unless you're going to print it off and color it, maybe this isn't the best one. Maybe what would work nicely too, if I could get up to my top bar here, I could put periodic table, metals, non-metals, and there's a good one right off the bat. So maybe even using this one isn't the worst one ever. Although this one, again, there's no information on it besides the symbols for the names. So this one might be good for classifying. Because remember, one of the things we're going to talk about here in a little bit is whether something's ionic or covalent. And being ionic means it has a metal in it. So if you can just find the symbol with the metal, then you can be able to tell. But anyway, got the periodic table ready for you. Now where to go? Okay, here it is. Let me taking a quick snapshot of it. Okay, so here is our periodic table. And where'd my pen go? There it is. Okay, so right away, intro to the periodic table, we started talking about some things we needed to know. We talked about families or groups. These are running up and down on our periodic table. And we labeled them 1, 2, 3, 4, 5, 6, 7, and 8. And those numbers did end up meaning something to us in a little bit here. We also talked about rows running this way. And periods, I guess we call them periods. That might be a better name. And we have 7 of them on the periodic table. That just told us how many shells we've got when we get to that stuff here. So there's your periodic table. I think the very first thing we did was we talked about metals, nonmetals, and metalloids. Maybe we should just revisit that quickly. And so when we're talking about a metal, you know, we talked about some physical properties. We said that metals are gray or silver in color. We'll just make a quick list here. So again, when you look at a pure metal, what are you looking at? You're looking at something that's solid. It's hard. It's got a high boiling point and melting point. High BP and MP. They conduct electricity. I'm sure there's a couple other ones you guys can think about too. Anyway, those are just a quick little list of the physical ones. Now, chemical ones, again, these are the ones where you have to do an experiment. We found that metals are very reactive. They react with water. You know, they'll rust, they'll explode. they'll react with oxygen. They'll corrode, they'll change color, or lastly, they'll react with acid. And when they react with acid, they actually give off hydrogen gas. So those are all types of reactions that metals go through. So essentially, metals are fairly reactive, I guess. They're hard, they're stable, but they're fairly reactive. When we compared them to non-metals, we found that they were just kind of the exact opposite. So if we talk about some physical properties of non-metals, you know, if metals were gray, then we found these to be colorful. If we found these metals were solid, these ones are solid, liquid, or gas. They can be all three. They tend to be soft. They're brittle. They do not conduct. That's why you can grab the handle of a pot. Anyway, those are some of our physical ones. And then when it came to chemical, we found that metals were reactive, and these were not reactive. Again, it was all about being all the opposite of our metals. So that was the first thing we did. We also, again, like I said, colored the periodic table, and that sort of came back in a little bit. So make sure when you get to do this exam, you at least have a periodic table opened up that has the metals and non-metals colored, like the one I showed you. That's probably a good thing. So once we'd done that, our next step was we started to talk about atoms on the periodic table. One quick adjustment for me here. I could really do a nicer job writing if I put this down flat. Okay, so atoms. So we're talking about what's inside of the atoms. So we found that atoms contain electrons, and these are found orbiting the nucleus in shells. Remember, we drew some Bohr-Rutherford diagrams, and we'll get to those in a little bit. So they contain electrons that are, I guess they're negatively charged. I didn't really say that. They also contain protons that are positive. And this relates to our atomic number. We'll come to that in a sec. And we also found that they contain neutral neutrons. And these have no charge. And both of these particles are found in the nucleus. So one of our goals was to figure out how many protons, electrons, and neutrons that different atoms have. So just jumping, I'm going to steal my periodic table here for a sec. So I'm just trying to expand this a little bit so we can see fluorine. That's always my classic example here. So here is fluorine. It is number 9. That number is our atomic number. Whoops. I can do better. Okay, so number 9 is our atomic, no, that's worse, atomic number. And the atomic number tells us how many protons and electrons something has. I'll rewrite this on the next slide. And we also worry about the number right beside it on this periodic table, 18.999. That's, we want to round that one. That's our mass number. We'll talk about that here in a sec too. I just wanted to point them out first. So that's our mass number there. So let's see here. Bohr-Rutherford, no, sorry, standard atomic notation. This was our first attempt at organizing that information on the periodic table. So when it comes to it, if we do fluorine, we had a mass number of 18.999 that we round. We put a 19 there. It had an atomic number of 9. We put that on the bottom, and we put the F there. So the F, that's just our symbol. That's really nothing. I'll label it, though. Symbol. So this 9 is our atomic number, and that's pretty important. That tells us our number of protons. Number of P's and E's. So it's the number of protons and electrons for a neutral atom. They all start off, every fluorine atom would start off with 9 protons and 9 electrons. And then 9 protons is carved in stone. If you find an atom in another dimension with 9 protons, we would call that fluorine. The fact is we also learned that electrons can go up or down. 19 is our mass number. So that's the mass of an atom, and that's all found in the nucleus. That's our number of P's and N's, so number of protons and neutrons. So one thing, once we already found the standard atomic notation like this one, we would say, okay, if this is number 9, it has 9 protons. There's nothing here about a charge, so I've got to assume it has 9 electrons. And then figuring out our neutrons, we just need to subtract the 2 numbers given, and we get our 3 particles. So we spent some time with that. So that's standard atomic notation. We use standard atomic notation to go into the Bohr-Rutherford diagrams, which were just pictures showing where all the electrons are drawn, because there doesn't really appear to be any electrons in this example. So again, being that this exam is just like our quizzes, it's online, it's multiple choice, matching, true and false, that's those style of questions. We're not going to have to draw any of these, but I do have a couple pictures of these, and I want you to just get some information off of it. So the Bohr-Rutherford shows where electrons are found, and we can put 2 electrons in the first shell, and then it becomes full, and 8 electrons in other shells. So that was our rule for drawing these. So even using that lithium example from earlier, we'd say, and we did say this earlier, that this one has 9 protons and 9 neutrons, so you can just draw a little circle around that. So what's going on here? We got 9 P's and 10 N's. We already figured that out earlier. And that's our nucleus. So those 2 particles are found in our nucleus. Because it's number 9, we have 9 electrons to put in this. So we said we could fit 2 in that first shell, if you will. 1, 2. Something's wrong with my pin here. There we go. If we started with 9 and we've already drawn 2, that means we have 7 left. So I can draw another shell and draw those other 7 in it. 1, 2, 3, 4, 5, 6, 7. And once we've drawn that properly, those are the 2 rules you got to follow. We talked about a valence electron. Valence electron. These are electrons found in the outermost shell. So we know that we just had 9 electrons in total, but if we actually counted up the ones in the outer shell, there'd be 1, there'd be 2, 3, 4, 5, 6, 7. This one only had 7. 7 valence electrons. Now hopefully you guys remember the fast way of finding valence electrons. It actually goes back to our periodic table that we looked at earlier. And remember these numbers? So anything in the first group has 1. Any of these has 2. Any of these has 3, 4, 5, 6, 7. So fluorine's in group 7 and it has 7. And then 8. So what I'm talking about here is I'm talking about our Lewis diagrams. What's that? Lewis diagrams. They just show the valence electrons. So don't forget, group number indicates the number of valence electrons. So if you're drawing something from group 1, like sodium, it's in group 1, so you just give it 1 valence electron. If you draw, say, calcium that's in group 2, you give it 2. If you did fluorine in group 3, you do 3. You got carbon in group 4, you put 4. When you get to nitrogen in group 5, you actually have to make a pair. And when you get to sulfur, it's got a couple of pairs. And then fluorine, like we just talked about, has 7 valence electrons, so it has 3 sets of pairs. And then when you get to the last one there, argon, it has a full outer shell. It's all nice, stable, and happy. So none of these ones that we just drew are actually happy. It all comes down to the octet rule, which talks about us gaining and losing these valence electrons. So only this one is stable. That's the only one that's happy. Just do one thing here, take a minor break. I know we're motoring along here. Okay. I don't think I want to talk too much about stable ions. Let's just say that atoms are only stable when they have either 0 or 8 valence electrons. So that means that they must be gained or lost. And so we spent some time figuring that out. But then we also, in the end, discovered that there was a really easy way to tell what the stable ion was of an atom, and that was, again, back to our periodic table. So once again, skipping back to our periodic table, let's pretend we were looking at stuff in, say, here, this group 1. We were just looking for those stable charges right there. So you'll notice that there's a whole bunch of +1s. So that means any of these atoms, their stable charge is +1. We're looking at group 2 here. These ones happen to be +2. Some of them in the middle have a couple of charges, +3 and +2. That's fine. And we can also have some negative ones. You can have, say, over here, we get chlorine with -1. These are all -1. You can have some -2s, -3, -3, and so on. So these are the numbers that we needed as we started talking about ionic and covalent, and that's kind of where I want to lead up to and end here. So this is, I guess, maybe our third part. So this is naming and drawing compounds. So ionic compounds. These are made of a metal. The metal comes first, and a non-metal. The non-metal comes second. So another way of saying this is it's made of a cation that's positive and an anion that is negative. So if we want to, say, create a formula, and that's one of the key things we wanted to do here, so let's say we had sodium, and if you go back and look up sodium, it has a stable charge of +1. And let's say we do it with sulfur that has a stable charge of -2. So this is sort of our crossover method we talked about. So to figure out the formula of this compound, all you need to do is you need to write the first symbol, and then look to the number of the other symbol. It comes down, and it tells you this one has 2 sodiums. Then if you want to know how many sulfurs you got, you just look at the number with the other atom, and that tells you get 1. So you don't write them in. And then in terms of naming, you write the first symbol, which is sodium, and then you take sulfur and you add it to have an "-ide" ending, sulfide. So sodium sulfide. That was our crossover method. We can tackle a few more of these. So let's say we had calcium with a stable charge of +2 and chlorine with a stable charge of -1. Again, those charges are on the periodic table. We kind of only use the ones on the right side and left side of the periodic table mostly. So if you want to come up with your formula, you write calcium. You say, okay, what number is with chlorine? It's a 1. There we go. Again, we don't usually write the 1 in because it's already understood to be there. And then if we want to figure out how many chlorines there's going to be, that 2 comes down. We get a 2 there. So to name this one, name the first one regular, calcium. Chlorine becomes chloride. Maybe one more. We have aluminum and oxygen. What was that? So if you want to know how many aluminums there would be, you look to the number with oxygen. It comes down, there are 2 of them. If you want to know how many oxygens there's going to be, look at the aluminum number, 3. That's it. Aluminum oxide. So these were all ionic compounds because they all started with a metal. Calcium, aluminum, sodium, those are all metals. One of the questions on your test is they say, are these compounds ionic or covalent? And you just got to look it up. Does it have a metal? Yes, then it's ionic. So ionic compounds have metals. Forgot how to spell metals there for a minute. Now covalents are a bit different because they're all nonmetals. There's no crossover here. Made of all nonmetals. No crossover. Method. This was the prefix method we needed. Prefix. So to hit those quickly here. 1 was mono. 2 was di, 3 was tri, 4 was tetra, penta, hexa. By the way, in grade 10 science, you'll see all this stuff again. So once you've identified your compound as being covalent, you might identify it because you actually see some of these names. So if you actually see some of these names here, using mono, di, tri, and then you say, okay, it has to be covalently bonded because it has that stuff in it. Now the reason we need these is because you can have a couple of different examples here. So CO2. So if you totally forgot about naming covalent compounds, you might call this carbon oxide. That's not right. It's not right because we have all nonmetals. We would, and seeing this one, it's called carbon dioxide. Now again, there was no pluses or minuses. There wasn't anything crossed over. This is all about electron shell overlap. So there are different combos that can come out. So you can have carbon dioxide, but you can also have the gas that we have a detector for in our house, carbon monoxide. So you can have different combos here. I mean, we could have C3O4. Again, they're all the same atom, the carbon and oxygen, it's just in different combinations. With ionic compounds, there aren't different combinations. There only ever is one. If you have sodium and chlorine go together, it's just NaCl all the time. You don't get different numbers. So with this one, this is where we need our tris. We have 3 carbons, so we put a tri in front, tricarbon, and then there's a 4, tetraoxide. And that, I think, about wraps it up. I know there's a ton of stuff there. So hopefully you stuck with this. It's probably a good time now to go and check out the chemistry practice exam. Lots of people here, that's good. Again, so that is listed on your home page. You can do that there. Why don't you go try it a couple of times? That's fine. I would also recommend you guys go back and check to see if you have any chemistry quizzes that you need to do. More in quizzes. Now, back in the chemistry unit, we used to have 24, 28, 20, 23. Look at all these attempts at comp. We had some naming ones. They were all over 20s. That's when people were paying attention. Now look what's happened. The biology, 9, 8, 13, 14. We have not had a 20 quiz until the second biology one. Look at that. A lot of single digits here. It's been forever since we had things in the 20s. Look at this. Lots of 20s for the first half. That means people were doing both attempts. And then very few after that. I think a lot of the time it was you do it, you get 2 out of 10, you'd be like, yeah, good enough. Well, it's not good enough. I want you guys to do better. Again, I updated all the marks the other day. And you guys can go and check your marks if you want.